Alright, so in this particular video, we have an airplane that's flying horizontally initially, and it's going to drop a package as demonstrated here in the schematic. Okay, so for this particular 2D or projectile motion problem, I do want to point out that Vx stays constant because there is no acceleration in the x direction. However, there is acceleration in the y direction because gravity is going to cause the package to accelerate downward. So it's important to kind of pay attention to each of these locations in the diagram based on the initial point. So here initially, there's only Vx, which is the initial velocity of the airplane. But if you drop a package, the package will have the same initial horizontal velocity as the airplane. So if the airplane is moving at 115 meters per second, the package will have that same initial velocity. But once it leaves the airplane though, gravity will cause it to accelerate downward, as indicated here or depicted here using these vertical velocity vector components. Okay. All right, so let's do it. So if you need to, pause the video and then read all the different parts here. All right, other than that, I will go ahead and show you how to do all these different parts. Part A asks us to find the time required for the package to hit the ground. This one is pretty straightforward. Okay. To do this one, I'd encourage you set up this X and Y chart if you need to start. Hopefully, once you're good at it, you can kind of skip this entire process. Here at the very top, this is a quick reminder that the acceleration in the horizontal direction is 0. The acceleration in the y direction is simply acceleration due to gravity, which is negative 9.8 meters per second square at the surface of the planet, or near the surface of the planet. All right. So in order to find the time, it's important to focus your direction in the y direction, only because the object's accelerating downward, not horizontally. So I would just set this up. Delta x is equal to VIXT. You notice here the 1/2 AT square in the horizontal direction is no longer present because AX is 0. So that 1/2 AXT square would simply cancel out. So I left that out of my work here. So the horizontal displacement is simply the initial velocity in the horizontal direction times time. All right. I'm going to set up the y direction. My vertical displacement function is VIYT plus 1/2 GT square. It's important that for this particular unit, you need to differentiate that there is an initial velocity, there's a VIX, and there's also a VIY. Sometimes things can be the same, but sometimes things are different. So in this particular problem, my VI is 115 in the diagram, which is also my VIX because the vector is drawn horizontally pointing to the right. All right, so let's knock it out. In order to find part A, I'm going to focus my attention in the on the right side here, only because I have a lot of information here. Delta Y is given in the schematic as negative 1050. The package is falling down, so the vertical displacement needs to be negative. I know my acceleration due to gravity is negative 9.8, and then therefore we need to simplify our work. 1/2 times negative 9.8 is negative 4.9. And then to get t squared by itself, divide both sides by negative 4.9. Or in this case, you can just cancel out the negative sign if you like. Negative, negative makes a positive. So here we have 1050 divided by 4.9 equals t squared. And then we can simplify that. 1050 divided by 4.9 will give you about 214.3. And that's equal to t squared. Therefore, to solve for t, we need the radical both sides. So t is going to equal to about 14.6 seconds. I just round off to one decimal place here. Okay, so if you're doing your working, round up to 2-3 decimal place if you like your answer to be more accurate. All right, but the physics is that. So here, it takes about 4.2 seconds for the package to hit the ground. All right, let's move on to part B. Part B asks you to find the velocity v. I kept this particular variable v because in the diagram they call it v, but really it's v of t or v final, so depending on the schematic they might use different notation. But to me, this particular dashed line here, that's the diagonal. In this particular diagram they call it v, but you need to know that it's the same as v of t, but v of t is also your final velocity, which I like to use because I think it helps differentiate, what your initial and what your final positions are. All right. Therefore, to do this one, I will use this particular function, Pythagorean theorem. The final velocity square is going to equal to the final velocity in the y direction square plus the final velocity in the horizontal direction square. So essentially, you have a triangle to play with. Okay. All right, let's knock it out. We know VFX is given as 115. because ax is 0, the horizontal velocity for the whole entire trajectory stays the same. So as you can see in the diagram here, all of the v's in the horizontal direction stays constant because ax is equal to 0. So that one's pretty easy to do. So I'm just going to plug in 115 for vfx, and then that's going to be square. However, I need to find vf, but I don't know what vfy is. So let's go ahead and find vfy. Okay. In order to find VFY, I'm just going to focus my attention directly in the y direction. Here I have VFY minus VIY equals 2G delta y. So you notice there is a consistency here in terms of using subscripts. Here's VFY. If that's VFY, then I need to use VIY. And then if that's VIY, then I need to use delta y. It's important that you don't mix up your VIs. Again, so pay attention to information given and do not mix your X and Y information together in any given function. Otherwise, it'll jack up your answer, okay? In this particular problem, I can cancel out VIY only because the package is being launched initially horizontally, or aka released with the airplane, and the airplane is flying horizontally, so the package has an initial horizontal velocity direction. But not VFY, but not VIY. Okay. To find VFY, it's plug and chug. The 2 gets carried down. G is negative 9.8. Delta Y here is negative 1050 as given in the schematic here. And then that's it. We can just do a little calculator work. Negative sign makes positive. And then all this will give you a product of 20,580. But this is VFY, which is what I need. You know, sometimes you just have to figure out when to stop and when to keep doing it. Except in this one, I'll break it down a little more because I know it asks for velocity, which indicates that I need to find the direction, aka the angle. But to find the angle, I actually need the leg of this triangle. So I'll actually go ahead and square root it for this one. The square root of 20,580 will give you a plus minus 143.5. Okay, so don't forget when you square root stuff, you get a positive and negative answer. In this case, I'll use the negative because it's falling down. But if you're paying attention, it doesn't really matter because once you find the angle, it's kind of common sense. All right. Now, if you don't like using this particular strategy to find VFY, I direct your attention over here. I left my work over here because I can find this VY also using this kinematics equation. The final velocity in the y direction is simply g times t plus VIY. Again, not just VI, it has to be VIY. So be consistent with your x and y. Here, I know my VIY is 0 because it's being launched horizontally. I know G is negative 9.8. And then if you use the answer in part A of a time of about 14.6 seconds, you should get the same value as over here. Okay, so we got about 143.5 here. You notice your VFY is negative 143.1. That's because the time I round off to about 14.6. But again, if you want, you can recalculate it. And if you use a more precise answer in terms of decimal, you get about the same answer, about 143. How's that? Okay. All right, so that's 2 ways to find VFY. But we're not done yet. In order to find VF, though, we still have to do a little extra work. So I'm just going to carry my work down. VF square is going to equal to VFY square plus VFX square. But VFY square, watch my circling, VFY square, okay, it's just this value here of 20,580. Or if you want, you can plug in 143.5 and then square it again. You'll get the same value here. So make sure you pay attention to whether your value represents VFY or VFY square. I already have VFY square, so I'm just going to go ahead and plug it in here. And then 115 square is simply 13,225. I'll add those values together. And then that's 33,805. And then we're just going to square root both sides to get VF by itself. So you'll get VF as about 183.9. So I do want to point out that this value here is just the speed. Okay, it's just your speed. It's not your velocity. Your velocity has 2 components. It has to have a speed and a direction. Doing the math here allows you to find the speed. But it's important that you notice in the animation that just came up, you need to be able to give this angle. This is your direction. It's not good enough to say down. It's not good enough to say right. This diagonal is in the 4th quadrant. So it's important to tell someone that it's falling at a certain rate in a certain direction. Well, how do you find this angle? It's pretty easy. Just do a little trick. So here, my vector is going to move to the right. Okay, Vy here is pointing down, but I can just shift that same vector to the right so I can make a little right triangle. Theta here, I can just use tangent because tangent is opposite over adjacent. Okay, so tangent is opposite, which is this leg that's pointing down, over your adjacent, which is 115 meters per second in the horizontal direction. So essentially tangent is y over x. But here I have theta is equal to inverse tan of VFY over VFX. Again, tangent in geometry is just opposite over adjacent. Most of the time, if it's touching the x-axis, it's y over x. So here I have VFY over VFX. VFY, I already know that's 143.5. Here I've chosen to just use the positive value because I need to provide the direction, given the orientation here. Or if you want, you can put in the negative 143.5 and it doesn't change the angle itself. It'll give you a negative 53.3, okay? So, which is pretty much the same angle, which is how you want to state it. All right, other than that, if you do that properly, the angle comes out to be about 51.3 degrees southeast. If you choose to put in the negative sign, it'll give you negative 51.3 degrees, which essentially just tells you you're starting from 0 degrees on the unit circle and just go backward. So it's proper to say 51.3 degrees southeast, okay? Or below the positive x-axis if you choose to use that type of wording. All right, let's do part C. Part C asks us to find the velocity at 2 seconds. Well, this is pretty easy to do. To find the velocity at 2 seconds, here in the diagram, I kind of just put it right here. This is just more for visual. This is not drawn to scale. I kept the horizontal velocity component constant so that my red arrow is about the same length that the red arrow is given. Here, I know 2 seconds has gone by, so I know there's some sort of velocity in the y direction and it has to be pointing down. Again, not drawn to scale. I already know Vx. Vx is 115 for the whole entire problem. What I don't have is Vy, okay? So I can just go ahead and use the same strategy as last time. In order to find Vf, I need to use Vf squared equals Vfy squared plus Vfx squared, aka Pythagorean theorem, because really it's just the right triangle we're playing with here. And then just go find what you're missing. Vfx is 115, we know that already. We don't know what Vfy is. So 2 seconds later, we need to find this vertical component, okay? So it's gonna fall as it moves to the right, but how fast is it falling downward? And that's what we need to find out. So to find Vfy, for this particular part, I'm just gonna use this function here that I used in part B as an alternative method. Vfy is gt plus Viy. Well, Viy is 0 if I start back at 0 second, and therefore g is negative 9.8. Time here is 2 seconds from 0 to 2 seconds. So therefore my Vfy is simply negative 19.6, which makes sense because it's falling downward. That tells me that this arrow here that I'm tracing back and forth at 2 seconds is negative 19.6. Well, let's just finish our work real quick. Vfy is negative 19.6, but we need to square that, okay? So here in parentheses, I have negative 19.6 squared. I highly advise you to use parentheses. If not, you will get a negative value, and that will mess with your numerical answer, okay? Use parentheses at this particular junction, because if you don't use parentheses, you'll end up just squaring the 19.6, and this will leave you with a negative value, which is wrong. So you need to square negative 19.6. Okay, so punch it in the way I have it on the screen and you can't mess up. All right, if we add all those values up, you get 13,609, but that represents VF square. But we don't need we don't need VF squared, we need VF. So let's go ahead and square root both sides just to get VF by itself. If you do that properly, the speed here is 116.7 meters per second. But as for for the velocity, which means we need to find the angle. So to find the angle, we just found that this particular vertical component is negative 19.6, and we'll just use the same strategy as the previous part. To find angle, I like to use tangent. Tangent of theta is inverse tan of Vfy over Vfx. We found Vfy already is 19.6. Vfx is given to us for the problem. Here, again, I've used 19.6 instead of negative 19.6. If you want, you can plug in negative 19.6. You'll just get a negative 9.7 degrees. So that's up to you. I'm just going to say that the angle here is 9.7 degrees southeast, or 9.7 degrees below the positive x-axis, okay? All right, so that's that for part C. So that's the velocity. The velocity has to have a magnitude and a direction. All right, now let's do D. Part D asks us to find the velocity at 3.7 seconds, okay? So here in the diagram, again, I've just provided a visual for you. To find the velocity, you need the Vx and you need Vy, or Vfx and Vfy. Here, we already know what Vfx is, which is 115. We don't know what the vertical is, so let's go ahead and use the same strategies as last time. I'm just going to go fast here. Vfy can be calculated using the same function as last time. I cross out Viy because it's 0, g is negative 9.8. Here, time is just 3.7 seconds. So really it's the same work as the last time, except the interval here is 3.7 seconds instead of 2 seconds. All right, if you simplify all that, you get negative 36.26, and then you carry this work down, finish out Pythagorean theorem. So again, use parentheses, negative 36.26, square it, punch it in the way it is on the screen with parentheses. This way you actually add and not subtract. And then if you do that, Vf squared is equal to 14,539.8 roughly. And then we need to square root both sides. Square rooting 14,539.8 gives you 120.6 meters per second. And that is your speed. Well, to find the angle, that's easy to do. We already found Vfy after 3.7 seconds is negative 36.26. So here in the diagram, I already know my horizontal vector, which is 115. I just found my vertical vector, which is negative 36.26. So there's that. Now that you have two legs, you have your horizontal leg and your vertical leg, just do Pythagorean theorem. So if we do our Pythagorean theorem, we found that it was 120.6. But now that we know the two legs, it's super easy to find this angle, right? Just use tangent. You can use sine, you can use cosine if you want, but I like to use tangent here because I already know Vx and Vy. All right, so inverse tan of Vfx over Vfy, which is 36.26 over 115. If you do it on your calculator, you should get a value of 17.5 degrees southeast. So you notice here as it falls, the angle keeps getting bigger and bigger. The angle opens up because Vfy keeps getting bigger and bigger. So the vector keeps getting steeper and steeper. So which makes sense. First, the vector for the velocity is perfect horizontal, but as it falls though, it turns. Okay, so if you can visualize like an arrow, like a Robin Hood arrow that's being shot up, as it spends time in the air, the arrow will tilt and it gets steeper and steeper. So as time progresses, it eventually approaches pretty much straight down, which is, we say that it approaches Vy as time increases. That's long enough, okay? All right, so that's the answer for part D. Part E, find the total horizontal displacement. To find delta x, so here in the diagram, the package left from the top, but it's going to go from left to right side of the screen. So the orange arrow here represents my delta x. To find delta x is just Vxt. We know Vix already, which is 115. We know our time from part A, which is 14.6 seconds. Multiply that, and you should get about 1,679 meters. So the horizontal displacement is 1679 meters east. Okay, since it asks for displacement, which is a vector, I will go ahead and say that it's 1,679 meters east, or positive 1,679 meters. All right, so that's that. So do not forget to include the direction. Now, if it asks for the horizontal distance, then just say 1,679 meters. Leave out the direction. All right. Now, part F though. Part F is easy to do. Okay, part F super easy to do. This one is a little tricky, but it's not that bad. It says, what is the instantaneous speed, aka the absolute value of V? So here essentially it says, don't find the angle. Just tell me how fast it's moving when the package is 300 meters above the ground. So here, this black arrow that's just bounced off on the screen, not drawn on a scale. This says it wants us to find how fast it's moving 300 meters off the ground. Well, that is 300 meters about. Okay, not drawn on a scale again. This is just to help you visualize things. Therefore, we know that this black arrow that just came up is 750. Well, how do I know that? Because the total height measured from bottom to top is 1,050. Well, it wants us to find the velocity 300 meters above the ground. So that's fine, which implies that it has fallen 750 meters. So I think it's important that you understand how to use numbers and not just look at numbers in a problem and just plug it in. This would be wrong if you just plug in like delta y is 300. Okay, so it's 300 meters from the ground up, which implies that the package has fallen a displacement of negative 750. Or a distance of 750. All right, so let's do it. To find Vf, again, we just need Vfy squared plus Vfx squared. We know Vfx already from the diagram. Here, we have to find Vfy squared. But to find Vfy, we can use this kinematics equation again. I'm going to cross Viy out. Here, 2 carry down, G negative 9.8, but delta Y is negative 750. It's negative 750 because it has fallen a displacement of 750. Negative 750 is fallen down, okay? So it's important that you get that negative sign right. Otherwise, you can't square root a negative number. You get some imaginary number stuff, which is junk. All right. Here we have VFY squared is equal to 14,700, and therefore we can just carry this work down. Here, you notice I didn't square root this, okay? I did not square root this. I did not square root this because I know that I need VFY squared. And because it didn't ask for the angle, I don't need to square root it because I don't need to know what the leg is. I just need to know what the Pythagorean theorem function is. All right. So therefore, VF squared is equal to 14,700, which represents, VFY squared. And then 115 squared is just 13,225. If I sum that up, I'll get 27,925. I'm going to square root both sides. Therefore, my speed is going to be about 167.1 meters per second. And because it asks for speed, I don't really care for the direction. All right, other than that, I hope that helps. Stay nerdy, don't be whack.